Okay, by now you should have invested plenty of time in knowledge review number 7. I'm sure you found it to be a great deal above and beyond what we asked for you in the other knowledge reviews, but let's stop and think about it. Knowledge review number 7, what is it really all about? Well, as we said in each of our knowledge reviews, it's taking everything that you've learned all the way up to the current section you just finished. And what did we just finish? Well, we finished Object-Oriented Programming 2. So by the completion of Object-Oriented Programming 2, you've got a strong understanding of how to work with classes, how to work with inheritance, how to work with polymorphism, and of course you've got a lot of the language fundamentals under your belt. What am I talking about with language fundamentals? Well, think about knowledge reviews 1 through 6. In 1 through 6, we were learning the C# language, the basic fundamentals of the language. Now, with Object-Oriented Programming 2, in this past section, we really started to just tie everything together. And with the techniques that we introduced to you through the use of polymorphism, inheritance, etc., you can really start to create some very powerful applications. So you were probably expecting a knowledge review that went something like this. Hello and welcome to Knowledge Review number 7. In this Knowledge Review, we're going to ask of you to create the following classes. Create a class, extend the class, inherit some stuff, override some stuff. You know, that's all fine and dandy, but to be honest with you, you guys are now getting to a point where you have close to 60 hours of content under your belt. You've gone through almost 100 videos, and to be honest with you, a lot of the C# language, you now have a good understanding of. So let's take the fundamentals of C#. Let's take the whole idea of object-oriented programming. Let's marry these two things together and let's start producing some more serious applications, because that's what it's time for us to do. It is time for us to get away from basic language lectures and start focusing on larger scale applications. So an introduction to this DAG, let me go ahead and write that back down, our directed acyclic graph application. And trust me, DAGs are very handy. You'll find them in 3D applications as we demonstrated in the last video. You'll find them in games. You can find them with complex data management. You can find them all over the place if you just look carefully. And with an understanding of how to create DAGs, you guys are going to be set up for doing some very sophisticated things later on in the XNA class. But starting with the DAG, here we are, asking you to create a far more sophisticated program than anything you have created up to this point. You agree, Logan?
For sure. Everything up before has just been to test individual skills.
That's right.
This is where you have to go through and pull a lot of skills together into a single larger application.
That's right. Now, if you're sitting there right now extremely frustrated, staring at the monitor, thinking, yeah, I just want to grab this monitor and throw it across the room because I didn't get anywhere with this. Well, first of all, the pre-planning phase is critical. If you skip the pre-planning phase and you jumped right into Visual Studio and started coding, you just made a large mistake. Agreed?
Agreed. If you try to take that approach, you'll probably end up coding yourself into a corner.
That's right, because you don't have a plan of attack. And a plan of attack with an application of this size, even though it's not tremendous in size, I mean, it's still far larger than the things we've asked of you up until now. If you don't have a plan of attack, you're going to do, as Logan said, code yourself into a corner. You're going to get frustrated. You're not going to have an image of the bigger picture in your mind, and it's just going to all end up collapsing like a house of cards. And that's something that you really don't want happening, because then how are you ever going to start creating large and sophisticated games if you can't create something, well, as simple as this DAG application? And believe it or not, this application is simple if you break it down on paper first. Now, if you got the assignment, fantastic. That's awesome. If you did not get it because you went straight into Visual Studio and started coding, then I recommend in the future start your planning on paper first. Now, if you did plan it on paper and then you went into Visual Studio and you ran into lots of problems, hey, that's why we are here with the next set of videos. These videos are going to walk you through the creation of this DAG application. We're going to go step by step. But what we're going to do is we're going to present it in the form of, here's a series of hints or suggestions. And then after the hints and suggestions, you are more than welcome to pause the video and apply those hints and suggestions yourself. And then come back and watch how we did it and see if your implementation is the same as our implementation. And you'll find that you can easily go in different directions than us and end up with the exact same result. To be honest with you, I'm sure there's several of you out there that have accomplished this application in a far more elegant way than we've done it. We've tried our best to stick to everything that you've learned and really keep a tight rein on that. And I think we've done a pretty good job, Logan. Wouldn't you agree?
Right, using just the core set of skills that have already been covered
exactly
to put all this together, so we don't branch out into anything new. This is still just pulling on all existing skills in order to put a more complicated app together.
Oh, and I can promise you, while going through and designing this on a piece of paper, we definitely wanted to get into things that you guys have yet to see. But we did a really good job of keeping ourselves restricted. So, once again, you may have gone above and beyond and come up with different techniques of doing something, and if that's the case, fantastic. And if not, and again, you ended up in a corner where you're like, I can't get through this, just watch what we do here. We are going to implement everything you have seen in this course up until this point. So, as I said, we're going to start out with hints, and then from there, you can go and try it yourself. The hint in this video is going to be taking a look at the overall architecture, the node architecture itself, and how we want to, using everything you've been shown so far, implement a structure that will work and give us what it was we were looking for. Let's go ahead and get all those cute numbers off the board. Starting out with, first of all, you were asked to create a DAG, a directed acyclic graph, that was comprised of a series of transform nodes that could create a hierarchy. So let's go ahead and review that real quick, and then we'll take that information and start breaking that down into something with a bit more structure. So here we are with the creation of a transform node that I shall label TXFRM so that I don't have to do a whole lot of writing tonight. All right, so here we are with the transform node. Now, what is this transform node? It's just an instantiation of a class. That's all it is. So look at it as an object. Nothing more sophisticated than that. Except here we ran into an interesting situation where we could create a hierarchy of these. So here we are with another transform node, TXFRM, and we'll call this 2, where transform 2 is a child of transform. Then I could come over here and create another one. So transform 3 is a child of transform. And then finally, let's just jump down and do one more. So here we are with transform 4. And transform 4 is a child of transform 2. Now, our transform nodes, as far as we're concerned, are going to be nodes that are going to contain transform information. Transformation information such as where an item is located in the world, how it's rotated in the world, how it's scaled in the world. Now, we're not going to be getting into rotation and scale right now, but later on we will be talking about those things. As a matter of fact, we're not even going to be worrying about translation Z. We're only going to be worrying about X and Y for the time being. But with the architecture set up, we can easily add these things into our transform nodes. Now, along with transform nodes, we told you that they were going to be shape nodes as well. So these shape nodes will basically be linked up with a transform node. So let me find a way of drawing that here. So we could say transform 3 has a shape node. I'm just going to draw these with dashed lines just so that you will easily recognize them as shape nodes. So shape nodes, the idea of them is to represent data. The data could be in the form of a light, it could be geometry, it could be bones, it could be whatever, okay? A transform node represents hierarchical information and transformation data. So where the object is, how it's rotated, how it's scaled. So by using a transform node linked up to a shape node, let's call this a sphere, S-P-H-E-R-E. The sphere then knows where it exists in the world because of its transform node. So here we are with the world. And again, we're only going to say that there is a translate X and a translate Y because we're only working in 2D at the moment. So transform 3 could say that its X is at 5 and its Y is at 5. Okay, so that means sphere 3 knows that at 5 by 5, that is where he would need to be. There is no transformation information that would be stored in a shape node. And we tried to make that as clear as possible in the last video. It just contains data. The data it contains in this particular case is this representation of a sphere. It's as simple as that. So now you can see the importance of having a transform node, and you can see why a shape node is linked, if you will, to a transform node. Now, you cannot have multiple shape nodes linked up to transform nodes. We talked about that as well. Each shape node has to have its very own transform node. So now if we had a cube, so we'll call this cube, and it happens to be at, say, 10 by 10. So we'll come over here and just say x is 10 and y is, well, we'll say 5. So here we are. We'll move over and we'll just draw him like right there. Okay? So the idea is to have the transform nodes represent where in the scene, and the shape node simply represents the data. But now, how do we take all of this and turn this into a system that's just code, where the code can represent this? Well, through a series of classes, obviously, and an intelligent use of lists. Because as of right now, you guys know how to use lists. So we can use lists to help manage these hierarchies. So how would we go about doing that? Well, before we look at the breakdown of a structure that contains the relationship of all of these classes to one another, let's start by looking at how we can set up our classes. Everything is a node, okay? So what is a node? It's a basic building block. And at the most fundamental level of a node, what one property or data member must it have? A name. We need to be able to recognize this guy as transform, this guy as transform 2, this guy as sphere, if the names that I am indeed drawing inside these boxes are their names. So if we were going to create a hierarchy of classes now, we could start out with our base class being node. And node is going to contain a name data member. Okay, so I'll just say a name field. That means anyone who derives from node will have a name. Now, who is going to derive from node? Well, we know we need transform nodes. So we'll extend node into a transform node. And in the transform node, this is where we're going to contain things like translate X, translate Y, translate Z if we were doing in 3D, rotation, etc. Okay? It automatically has name because it inherits name. Now, a shape node is not going to extend transform node. Transform node and shape node are two completely different things. The transform node, this guy's responsible for our hierarchies, right? Our shape node represents, as I said a minute ago, our data. So over here, let's go ahead and put shape node. And he is going to represent data. So these two guys definitely very different from one another, but they do share one thing in common. They are both a node. They both have a name. Okay? Now, there is some relationships back and forth between these two guys. If you think about it, the shape node is always tied to a transform node. Always tied to a transform node. So somehow the shape node is going to need to know about a transform node. So in his fields, we're probably going to want to set something up like a transform node. I'm just trying to decide where I want to write this at. So I'll put a transform node. So with transform node, we can actually point to the transform node we're linked to, if you want to look at it that way. Now, just for convenience sake, we could simply say that a transform node, if we look at it in the opposite direction, it'd just be convenient to be able to quickly tell who was linked to me, what shape node was tied into me. So we could, with the transform node, give it a shape node. So, and again, we're talking about a field, so we could have a shape node over here. So with the shape node, we can quickly find out what instantiation of the shape node we're linked to. So we can go back and forth quickly. So that's pretty cool. Now, shape node, we can extend even further. And this is where things get very convenient for us. We could come down off shape node and create geometry. So here's a geometry node. And we could create lights. We could create deformers, we could create bones, there's all sorts of different things that we can create. The bottom line is all of these particular type of nodes are shape nodes. If I wanted to create a light in my scene, and my light is, of course, casting light out in a particular direction, illuminating specific items. Ooh, what do you know? In this case, it just happens to be lighting up both of my spheres. Well, this light, to even exist inside the scene and be shown, it has to have some sort of position information. Translation information. So here we go. Obviously, the light would need to have a transform node. So in this particular case, we could say that transform 2 was linked to our light. We'll call it a spotlight. So where was our spotlight located at? Well, he was located down here at this particular area. Okay? Right there. And that data was provided by transform number 2. Right, if I can find where my pen went, there we go, right over here. So, hopefully by now you can start to see the relationship that's tying back and forth between the hierarchy that we are demonstrating on the left-hand side and the classes that we're demonstrating on the right-hand side. But now that we've got these classes being set up, how do we actually represent the hierarchical structure of transform nodes? So if you look at the whole class thing, the whole idea of a hierarchy resides where? It resides in transform node. It doesn't reside in node because shape nodes play no part in a hierarchy. It doesn't reside in light nodes and geometry nodes because they are indeed shape nodes. So you're going to find all of the hierarchical information inside of transform node. Does that make sense, Logan?
Right. The transform node is what's going to make up the hierarchical architecture or network.
That's right.
That's going to make up the whole parenting position network. Shape nodes or any other kind of node has no bearing on either position or how it appears in the hierarchy. So basically the entire hierarchy is built out of transform nodes.
You got it. So let's see. How do we want to demonstrate? I know. This is what we'll do. I am going to bring up a new whiteboard. We'll hide this one away. And let's start creating the following. Let's just take a look at some things that actually exist. Like, let's see, how do I want to draw this? So here we are, guys. We are in the design phase right now, and I am planning this out on a piece of paper. I'm going to draw for you the original drawing that I created on a piece of paper. That played a vital role in the start of the way that this whole thing is put together. So this box right here is going to represent our transform type object. This is going to be, I'll just put it as our transform node class. Okay, so this guy is the type object that's sitting over in the heap. Now, of course, we can have instantiations of this, but this is the actual class that's sitting over in memory. Okay, let's go ahead and draw the shape node sitting over in memory. All right, so far so good. Now, let's say that we were to create an instance of the transform node. So let's draw an actual instance. So we'll just come over here to the side. So this is our transform node. And let's give this guy a name. Let's call him TXFRM1. So TXFRM1. That's his name. Let's go ahead and create one more of them. It's about right here. Looks good. And again, this will be a TXFRM node, whose name in this particular case will be TXFRM2. All right, simple enough. And let's say that we have a shape node created as well. So we'll put a shape node down here somewhere. So shape node. And let's call this guy maybe sphere 1. So sphere 1. All right, excellent. Now how does all this tie together? Well, first of all, let's draw a very simple hierarchy using transform 1, transform 2, and our sphere shape node. So over here, we can say that at the root level, we have TXFRM1. Parented to him, we have TXFRM2, and let's just say that the sphere's transform node is transform 1. So I'll just do the little dashed lines. And so this is our sphere. So sphere 1. All right, so there's the hierarchy that I want to represent here inside of memory with all of these classes. Well, the first thing I'd like to do is I would like to be able to keep a static list of all of my transform nodes that exist at the root. Because at the root, we can have different hierarchies. Let me show you what I'm talking about. Let's go ahead and come all the way over here to the side, scroll down, and let me sketch this real quickly. I could have... So we'll call this transform 1, and he could have transform 2, and that's just absolutely horrible. Here we go. I know I said I'd do it quick, but not that quick. Transform 3, which has another child, transform 4. Now I could have transform 5, and I could have transform 6. Maybe transform 5 has one child. We'll call him transform 6. And this guy, transform 7. And transform 7 has no children whatsoever. So here we are with 1, 2, 3, 4, 5, 6, 7 different nodes in our scene. If I want to quickly find out who all of my root level nodes are, who are they? Well, they would be transform 1, transform 5, and transform 7. So I would like some way to manage, to keep up with who all of my root level nodes are. So we'll just come over here and call these our root nodes. Okay? Easiest way for me to do that, thinking about this, would be to have one master list of root nodes that I can get to at any time and simply say, give me a count. How many do we have? Or let's walk through them and check out all their names. Or whatever. There's all sorts of things we can do with it. So how about back here with our transform node class, we create a static list, which means all we got to do is talk to the transform node itself, the class, not an instance, and say, hey, yeah, your list. Tell me who's in it. So how about we come in here and we say list of roots. So we'd probably call this list something like root list or something.
Or root nodes.
Or root nodes. Yeah, in fact, I like root nodes better. It makes more sense. So I'm just going to represent that list as a box inside of the transform node class. And we have at this moment, taking a look back over here at the hierarchy that we've created, how many nodes do we have that are at the root? We have 1. Transform 1. Remember, you can't look at shape nodes when you're talking about root nodes. When you're talking about the hierarchy, you never look at shape nodes. You're just talking about transform nodes. So let's go ahead and put one guy in this list. Inside this list right now, we have TXFRM1. Now, we have just created a reference, right, that points over here to this guy. All right, simple enough. So at this point in time, I want to say, who's all at how many nodes do I have at the root? Well, I can query the root nodes, and I would get 1, because there's one item being stored in the list. And then I can say, all right, give it to me. And then I'd simply get a copy of that reference. And then that reference is pointing over here to TXFRM1. All right, simple enough. Now, I have this linkage between shape nodes and transform nodes. So inside of well, let's do this. I'm going to add it to both. Let's start out by adding over here a box. Okay, so this is a field inside of my transform node, which means there's obviously going to be one in this transform node as well. And these are the shape node fields. So in transform node 1, it's linked up, to sphere 1, to a shape node. So let's go ahead and put SPHERE, sphere 1 in here. So what have we just done? We have just pointed ourselves over here to this guy. All right, very nice. Now, in shape nodes, we need to also know who, in regards to the transform node, we are linked to. So let's do the same thing over here. Let's put some linkage in. And this right here is our field transform node that is being stored inside the shape node. So inside here, let's just simply put TXFRM1, because that is who we're pointing to. So over here, jump over. We are also pointing up here to the whole object. Okay? So very good. So far I can now see that transform 1 is at the root level over here. That's good. And through transform 1, I can see what shape node is linked to him. Very good. And with the shape node, of course, I can also look back to see what transform node I'm linked to as the shape node. Well, that's very nice. Now let's see if we can make this a little more interesting. We have transform 2 right now that is a child of transform 1. So we cannot take transform 2 and add him into our list of roots because he's not a root. He is a child of another transform node. So instead, how about I do something like this? I create a list of children. So that's list of children. Let me fix that T there. And let's draw it as a box, a longer box like we've been drawing. And let me fix that. And, oh man, that was the whole thing. I shall give you a much better box. There we go. That means, of course, down here with the transform node 2 object, I better do the same thing because these instances are the same. So list of children. So let's go ahead and draw this out. All right. Now that we have these lists, let's do something with them. So transform node 1 has a child. So let's put something in this list. It's going to be a reference to TXFRM2, to transform 2. So now we have just created a reference that points down here to this object. All right, very good. So now I have a way of actually telling who my children are. Sweet. All right, let's see. How can we make this even more interesting? Well, we saw that shape nodes contain data. So let's talk about rendering for just a moment. Let's say that we wanted to render out all of the geometry in our scene. Well, we don't render transform nodes, they just represent where items are at. Shape nodes represent the actual item that needs to be rendered. So I don't want to have to walk through all of my root nodes and then through all of their children to hunt for shape nodes to render. Because a transform node does not have to have a shape node. And we can see that right there in the illustration that I drew in the upper left-hand corner where transform 1 is linked up with sphere 1, but transform 2 is not linked up with a shape node at all. So to make it quick and easy for us to simply walk through all of our geometry, if you will, or let's just say all of our shape nodes, let's add a list over here to the shape node class. So this would, of course, be a static list called list of shapes. All right, so with list of shapes, let's go ahead and draw out a box for him. And right now, how many shape nodes do we have in our entire scene? We've got 1. And its name is sphere 1. Which means we are now pointing over here to this object. All right, very nice. So the convenient thing about having a list of shapes is at render time, I could say, let's walk through all of our shape nodes and draw them out. So as we walk through each shape node, we can quickly find out where they're located because every shape node contains direct access to its transform node through its private, which is what it will most likely be, a private field, or, well, it could be public, transform node. Okay, we'll get into the design of private and public coming up shortly. Right now, we're just designing, so we're just throwing terms around. But it looks like the design is starting to come along quite well. Let's see. Let's extend this. Let's go a little bit further now and see how well this system is holding up. So what I'd like to do is come up here, grab my tools real quick, and let's add a new color into the mix. And using this design that we've got in place, everything in red now is how we're going to enhance this. Let's say that I now have another transform node. And this transform node is called ball. And tied to ball is the ball shape. So we'll put in ball shape. Okay. And ball happens to be, well, let's put that away. Ball happens to have, let's see. I'm thinking. How about at the moment we just leave him just like that? So what's going to happen? He is a root node, so he would be added into the list. So now if I was to query on the root nodes list and say how many items are in there, it's going to tell me 2. Transform node 1 and ball. All right, so somewhere sitting out there in memory, we're going to need to have the ball transform node. So here we are with a transform node that is titled, its name is ball. And we also have a shape node whose name is ball shape. So let's see how all this ends up being hooked up. Well, there's going to be a list of children. And there's going to be the shape node field pointing at who we're linked to in regards to a shape node. So who's he going to be linked to? Ball shape. Very good. So that means we are now pointing over here at this guy. And we saw in here, he's going to point to the transform node that he's linked to, which is ball. And we'll just jump over that and finish off our line. There we go. So he's pointing over to ball. Very good. Well, we know since we now have a new shape node, perhaps we want it to be picked up quickly in the rendering engine. So since it's a shape node, he gets added into the list of shapes. So here we are with ball shape. So this gives us our squiggly line that references our ball shape. So far, so good. Almost done. Coming back up. This guy, let's just hop right on over there. And over these guys. And over this guy. Is pointing all the way down here. Very nice. Starting to have a whole lot of things starting to come together quickly. Oh, but let's go even further. What if, let's say, transform node 1 suddenly got another node that was a child as well? You know what? Instead of drawing it on that side, let me draw it on the other side. I like going from left to right. It's just a thing. And we will call this, give me a name, Logan, quick. All
right, box.
Box, I like it. All right. So it's another transform node. So let's instantiate a transform node real quick. So here we are, another transform node. That is called a box. And of course, inside he's got what? A list of children. So just trust me, that's a list of children. And he's got a reference to a shape node. So just for Logan, let's go ahead and create a shape node. So this is a shape node. That is called, we'll say box shape. So that's its name. So box shape is being stored over in the box transform node shape node field, and it will now point to the right place. Very good. Once again, we need to point back to it from inside here. So we're going to point to box from inside the shape node's transform node field. So he's pointing back over here to the object. Now, since box is a child, as seen up here in the upper left-hand corner, of transform 1, here's where it all ties together. That means we would need to come over here and add box into the list of children of transform node 1. So of course this reference is going to point down here to the box transform node. Since the box transform node had a shape node created with it, we need to add that shape node over here to the list of shapes in the shape node class. So this will be our box shape. And the box shape is going to point all the way back over to there. All right. So let's read memory and let's see what's in memory. right now, if we were to say how many roots, or excuse me, how many root nodes do we have? How many transform nodes exist at the top level of the scene? We've got 2. 1, transform node 1, 2. Let's make sure everything holds up. We query our list of roots inside the transform node class, and what do we find? 1, 2. And their names are right, transform 1 and ball. Fantastic. All right, let's just go ahead and move those out just because they're cluttering things up. That looks good. So now let's check to see how many children does transform node 1 have. Well, we see by looking at the hierarchy here, even though it's drawn a little cluttered, he's got 2. 1, 2. Both of these guys are children of transform 1. Follow their lines back. All right, well, let's verify in memory that that holds up. So we look at transform 1, and we check his list of children, and that list contains how many things? 1, 2, very nice, and they happen to be transform 2 and box. What do you know? Transform 2 and box. So that's right. Now let's check, are they pointing in the right place? So transform 2 points all the way down here. Yep, that's right. And box points all the way down to box. Oh, very good. So I managed to get the hierarchy right. That looks good for transform 1. So let's take a look at ball now. So here we are with ball. How many children does ball have? Let's turn our focus back to memory. So we need to look at the balls node. So here's the balls transform node, and its list of children. How many children does it have? None. There are no references in that list, so the count would return 0. Well, that works out really well. All right, very good. So just looking at our hierarchy, we got all the information that we needed from transform 1 and for transform 2 in regards to their children. Very good. Now what about their shapes? Transform 1 has an association with sphere 1. So let's just take a look at transform 1. So here's transform 1 right here. And he is associated with sphere 1. So he is pointing over here to the right object. Very nice. So let's take those out. And of course, sphere 1 points back to the transform node. So that works out beautifully. Transform 2. Who's his shape node? Looking down here at transform node 2, it's null. We don't have a shape node that we're linked to. Very good. So let's take a look at box. Does box have a shape node? Oh, let's just scroll on down. Box's shape node. Ooh, what do you know? Guess we could finish off our drawing up here, because we did say that it was a box. So this is, I'm just going to put BX shape. We all know that I'm actually meaning box shape. All right, so looking down here in memory it's right. In my graphical representation it was wrong. Isn't that funny? It just wasn't finished. So looking down here at the box transform node, we look in its data member for the shape node. So who are we pointing to? And we are pointing over here to the actual box shape node. And the box shape node is pointing back to box. Excellent. So all that's left is ball. Does ball have a shape node? Again, all I got to do is take a look at ball. And lo and behold, ball has a shape node pointing there, which is the ball shape. That's right. Who is pointing back to ball? The transform node. So that's right. So there is a quick look at, that's the whole hierarchy. That all turned out good. Now let's pretend we're a rendering engine. Rendering engine. Render out the scene. All right. Well, what do we need to render out? Simple. Let's take a look at all of the geometry we have. So the first thing we need to do is render out sphere 1. So we need to find out where sphere 1 is located at. So we follow sphere 1 down to here. Transform 1. We follow it up to transform 1. And we get our coordinates on where to render it out. Beautiful. Next thing we need to render in the list, because that one's now done, is going to be the ball shape. So the ball shape, once again, we come on down here. Oh, it's tied over to the ball. We follow it up to the ball, and there's our transform information. Render it out. So now we know where it's going to be rendered in the scene. Finally, our box shape is the last thing. And same thing for the box shape. Let's find out where is he linked up. All the way down here, who points back to box. And there is our X, Y, and Z coordinates. Let's render them out. So now we know where in the scene all three of these guys need to render. How cool was that, being able to simply walk through a list of shapes and not have to think about having to walk my way through a transform node hierarchy where some transforms may not have shapes. So now I'm having to ask myself, do you have a shape node? Do you have a shape? Oh, you do have a shape node. All right, well, let's render you. Do you have a shape? Oh, you don't. Okay, next guy. So we don't have to do all of that. Very convenient. Logan, is this all laying out pretty good as far as you being a witness?
Yeah, I think that maps out how everything should work very well. It maps out how data is going to have to be stored, how references are going to have to be stored for this type of hierarchy to work. And not only work, but to be efficient in the rendering sense.
Yeah.
Thus that one doesn't have to completely walk the network to find shape nodes.
Exactly.
One can simply find one can simply find shape nodes simply, and then immediately have access to relevant transform nodes, ignoring any that are for hierarchical positioning only.
Watch this, guys. Let's take this a bit further. It's going to make the screen messy. But what if we were to take this and parent ball to transform 2? All right? Let's see how it would work out. Check this out. What we would have would be the following. From transform 2, we would have ball, which would have the ball shape. So that's ball shape. Just trust me. All right. That means that right now, don't look at any of this. Let's pretend that this is no longer there.
That has been moved up under transform.
That's right. As a matter of fact, I'll use that to represent that has been moved to right here. Okay? Now, what has to happen in memory? Well, ball is no longer at the root, so it needs to be removed from inside my list of root nodes. So the reference is gone. I'm not going to be able to do a perfect job here, guys. Just bear with me. Ooh, that was actually pretty good. But, check this out. Ball gets added right here to the list of children for transform 2. So ball So it's still being pointed to. It's not like it's a lost reference and the garbage collector is going to come pick it up. So we're still pointing to it. So now, if I was to query the scene and say, how many root nodes do I have? Well, I only have one, transform 1. Looking over here, I only have one, transform 1. How many children does transform 1 have? He's got 1, 2. Okay? And that's correct. Transform 2 and box. How many children does transform 2 have? Well, let's take a look at transform 2. Transform 2 has 1 child, ball. What do you know? 1 child, ball. It works out beautifully. The idea is simply making sure that you manage these lists properly, that you add the references to the right lists, or if you have to shift them over to another location, you remove them out of the list that they were in. Otherwise, if I would have left ball up inside of my root nodes list and added it down here into my list of children for transform 2, I would have just created a problem for myself. This would not have been a good thing. So management of these lists is going to become very important. And this, believe it or not, is really simple. All you got to do is just make sure you put a little bit of thought into how you are constructing your methods to deal with the lists. Okay? So, and also check this out. By moving ball from the root to a child of transform 2, did I affect my shape node list? No, not at all. My shapes stay the same. Did I affect my ball shape reference? No. He still points over here to ball because ball is still the transform node that handles where he's going to appear in the world.
It's because we didn't do anything to the object on the heap. All we changed was the one reference from a list. That's just a reference. It's not going to affect the object itself, and therefore the reference from the shape is still going to be relevant.
That's right. So, ladies and gentlemen, this right here is a really good look at the system that I would like for us to create. This is showing you what is happening on the heap in regards to our type objects, both the transform node and the shape node, and all of our instances, okay? And we can see how basically we have these lists, and we're using these lists to point to our children. And that's basically all there is to it. So, Logan, is there anything else you want to add to this?
No, I think that paints it in a very clear picture of how this is going to have to work.
All right, so at this point, having seen this diagram here, and if we were to come back over here, this diagram, which started out by just providing a quick review on how the idea of transform nodes and shape nodes relate to one another, and how transform nodes relate to other transform nodes in regards to a hierarchy. Now that you've seen that, now that you've seen a representation of how we can create our classes in relation to one another, so starting at the base level with node, and then deriving a transform node and a shape node, and now you have seen how shape node needs to point back to a transform node, and a transform node, if it has a shape node, points to the shape node. So we've seen that now. And then with shape node, of course, we can then extend further into geometry nodes, light nodes, etc. Okay, all of our data items that can be represented in the scene itself. So now that you've seen this, if you have yet to accomplish knowledge review number 7, stop the video here and go ahead and try to implement some of this. What we're going to do in the next video is take a look at the requirements. What kind of methods are we going to need to have in place to accomplish what we just showed you over inside the memory with those diagrams just a second ago? Okay? So, once again, if you've yet to complete knowledge review number 7, see if you can use this as a direction pointer to point you in the right direction for creating this application. And perhaps that's all you need to provide the spark for you to create the entire thing. So if you're able to just start jamming right along with what we've shown you here and go from start all the way to completion, please do so, because this knowledge review will mean so much more to you if you solve it as opposed to us solving it for you and you just following along. So with that, Logan, is there anything else you want to add to this video before we wrap up?
Nothing I can think of.
Okay, so with that, that is going to conclude this video, which is a look at the node architecture. Thanks a lot.